Hello and welcome again to my channel. Our today's session is part 3 of our series here, Balancing of HVAC Systems, part 3, Balancing Method. Balancing methods are basically three basic methods, which we are going to talk about each of them later in this session. It is well known that in sizing a hydronic circuit, the hydraulic head of the circulator is calculated so as to provide sufficient differential pressure to the most disadvantaged terminal unit. Due to the pressure drop in the supply pipes, the loss of pressure of the different units is reduced in proportion to its greater distance from the circulator. Generally, the terminal units closest to the pump operates at an excessive differential pressure, thus risking the generation of an excessive flow rate. These closest terminals are facing a problem because they are closest to the pump, which is the circulator, and thus maybe they are facing problem of overflow. Now, to solve such a widespread problem, it is necessary to increase the pressure drop of the terminal units. In other words, additional resistance is required. The value of this resistance must be both known and changeable. The ideal device for practicing this compensation is the balancing valve, which also allows to verify that the calibration is correct when reading the instantaneous flow rate. Let us now consider this circuit here, in this figure 2.1, and suppose that the pressure drop between the pump and the most distance unit is 50 kPa, 50 kilopascal. If all terminal units are equivalent and each requires a differential pressure of 30 kilopascal, including pressure drops of the accessories and the control valve, the hydraulic head from the pump must be at least 80 kilopascal. In this situation, the differential pressure across the terminal units is between 0 and 50 kilopascal, depending on their distance from the pump. To compensate for the imbalance, it is sufficient to insert valves that can absorb such difference, which is balancing valves. The only exception is the most disadvantaged terminal unit, which having the exact differential pressure and therefore the exact flow rate, which does not need an additional correction. Before we go into details and elaborately for balancing methods, let's talk about some preliminary actions on the system before we do accurate balancing. To prepare any hydronic system for accurate balancing, we need to divide the distribution unit as much as possible into similar and homogeneous operational areas in terms of pressure variation and to which an automatic control system can normally be applied. Each of these areas must be defined based on the hydronic point of view: the pump, the control valve, the main distribution lines, the secondary branches, and finally the terminal units. We need to define the installation of balancing valves on the main columns, branch lines, and the major terminal units. During sizing of the automatic control valves that must control these terminal units, it is recommended to provide a differential pressure to the hydraulic head of the valves themselves to give an authority value greater than 0.5. For the control valves of the terminal units. Sizing is based on the different type of distribution. For installation in radiator systems, the thermostatic valve must be selected based on the differential uh, pressure of about 8 to 10 kilopascal in order to obtain fairly small kV values that ensure correct operation with any given pressure. For two-way valves, sizing must ensure pressure drop with a fully open valve and nominal flow rate responding to at least 50% of the differential pressure on the closed valve and at least 25% of the pump hydraulic head where possible. Sizing of the three-way valve must guarantee a valve pressure drop equal to the total pressure drop of all the element parts of the control circuit. For mixing valves, these items are installed upstream, for example boiler, while for diverts they are installed downstream, for example air treatment unit coil. Next, we need to calculate and size the pipe according to standard procedures. In particular, a contemporaneity factor must be considered in order to minimize pipe diameters. This coefficient should be identified pipe by pipe, and flow rates should be corrected according to the factor selected. An excessive pressure drop in the piping affects the smooth operation of the terminal unit control system, especially if we consider a variable flow rate distribution. We need next to choose the pump with total nominal flow rate and hydraulic head sufficient to supply the most disadvantaged circuit. Any overdimensioning is useless as the system will be balanced. Now let us talk about the sizing of balancing valves. A balancing valve, such as all passive resistances of a circuit, creates a pressure drop. This fundamental feature, if used in a proper way, enables to correct the differential pressure values and thus obtain the correct flow rate within the circuit. Passive resistances generate a pressure drop that modifies the flow rate according to the following equation. For the SI unit or SI units, dP is 10Q divided to kV total square, while where dP is in kilopascal. If it is in bar, dP will be Q divided to kV total square. The kV coefficient in a valve depends substantially on the section useful for the passage of a flow between the seat and stopper. This section provides the surface through which water can flow. The maximum kV value represents the flow rate in cubic meter per hour through the valve when the differential pressure is 1 bar between the upstream and downstream section of the valve. The balancing valve is generally chosen to have a desired setting value close to 75% of the valve opening. The flow at a lower pressure loss can be calculated by rearranging the equation KVS equal to Q divided to delta P, where KVS value is calculated by the unit square cubic meter per hour. Q is the flow cubic meter per hour. Delta P is the pressure differential across the regulating valve pipe. This allows to get the maximum precision while keeping investment costs under control. Normally, the diameter of the valve can be less than the pipe diameter in existing installations. It is often difficult to calculate the required setting value. In order to avoid overdimensioning, it is recommended to check that in fully open position and with nominal flow rate, the pressure drop is at least 3 kPa. Now for the first method of regulation method, which is called pre-regulation method. This method is a calculation method to define the balancing valve setting in advance when sizing distribution lines based on the nominal flow rate and pressure drop of each circuit. The pump is selected to meet the needs of the most disadvantaged unit. Its hydraulic head, which is able to supply this unit, generates therefore undesirable overpressure for the other units, thus causing excessive flow rates. We have to do this step in all the components of the circuit, including the circuit itself and the control valves and localized pressure drops, supply and return pipes for the chiller. Next step, we have to repeat this operation for all circuits in parallel with comparing the values obtained and identify the most disadvantaged ones. So a similar result can be obtained by calculating the differential pressure obtained at each node of the main line and by sizing the balancing valves based on the difference between the dB and the node and at the node and the one required for the branch. We will see this in this example here, as we see in this circuit. For example, here this circuit consists of 3 coils and one circulation pump, and there is circuit delta H here, circuit delta H, and there is dP for total circuit, and for each coil there is a dP, and for all the components here there is dP, delta pressure, differential pressure. And let's see how to calculate this, how to do these steps. We can do this meaning of this sentence. A similar result can be obtained. Here the nodes, 1, 2, 3, 4 nodes. We can calculate for each node and we can get the same result if we consider the circuit itself with its component individually and the nodes. We can get the same result, and we will see how in this. So on this circuit we have total flow of 19 cubic meter per hour, and individually it is branch here for this coil getting 5 cubic meter per hour, and this branch the other two branches are getting 7 each, 7 cubic meter per hour flow. So if we consider this, so the coil 1 here has a Q 5 cubic meter per hour and dP is 20 kPa. Let's consider it 20 kPa. And coil 2 and coil 3, each of them 7 cubic meter per hour and dP each 30 kPa. So in the pipe A here, in the pipe A, let's calculate also here. Consider this pipe A from here to this node. This is pipe A. Pipe A has total flow of 3 coils, which is 5 plus 7 plus 7, which is 19 cubic meter per hour. This pipe A has differential pressure 15 kPa considered. Pipe B here from this node to this node is equal to pipe E from this node to this node, and the flow for this pipe and the flow for this pipe is 14, which is equal to 7 plus 7, and the dP differential pressure is 8, considered as 8. And the last pipe which is the here in this circuit, which is the coil 3 pipe from C this pipe C, which is considered from the node to the first resistance, which is equal to D, which is from the node to the first resistance here, is equal. The dP is equal. The flow is equal. Flow is 7, and the dP is 8 kPa. So next will be the balancing valve is installed in series with the most disadvantaged series is, in this situation, number 3 has diagnostic function and is selected to have lowest possible pressure drop, however not less than 3 kPa as we discussed before. And to ensure accurate reading with the differential pressure gauge based on the setting parameters given in the technical sheet from the supplier, the diameter and setting values are defined as follows. Static 3, static balancing valve number 3 is 2 inch, set to position 90 with dP 6 kPa. So we will consider this static number 3 2 inch with setting 90 and dP 6 kPa. So considering this, flow rate Q, total flow. Now we can define the operation characteristic of the pump. The total characteristic of the pump is equal to the 3 coils, which is the flow in the coil number 1, flow in the plus flow in the coil number 2, plus flow in the coil number 3. And the differential pressure in the pump is equal to the hydraulic head H. So the total flow is Q coil 1 plus Q coil 2 plus Q coil number 3, which is 5 plus 7 plus 7, which is equal 19 cubic meter per hour. While the hydraulic head is, as we can see here in the diagram or in the circuit, it is pipe A plus B plus C plus coil number 3 plus static number 3, which is here, as we can substitute the figures, as we say A plus B plus C plus coil 3 and plus D plus E, because we are coming back to the end of circuit here. So if we substitute the figures here, we can get 15 plus 8 plus 8 plus 30 plus 6 plus 8 plus 8, which is equal to 83 kPa, which is delta H here, delta H here, we can say. Now, according to the first system, the total dP to each unit can be calculated considering the entire route from circulator to circulator. What this meaning? According to the first system, the total dP for each unit can be calculated considering the entire route from circulator to circulator. For example, if you are calculating for coil 1, so this is circuit number 1. If you are calculating dP for coil number 2, this is circuit number 2. If you from circulator to circulator, if you calculate the dP for coil number 3, it is this circuit from circulator to circulator. So for example here, circuit number 3 dP is equal to A plus B plus C plus coil 3 plus static 3 plus D plus E, which is exactly equal to delta H 83. If you substitute, it will be the same, because For coil number 3 here coil number 3, it is A plus B plus C plus D plus coil 3 plus static 3 plus E, same as delta H. If you can, we have to note that in this circuit we consider static 3, but in other circuits here, if we are going to calculate for coil 2, we should not consider static 2 and static 1 here, as we can see here. Circuit 2 dp A plus B plus coil 2 plus E only without static 2. Circuit 1 as well, it is total dp which is equal to A plus coil 1 only without static 1. If you substitute these figures, you will get 61. This is actually, we have to explain it a little bit. Static in coil 2, for example, it is A plus B plus coil 2 plus E only. In coil number 1, A plus coil 1 only. So if you substitute these numbers, you will get in coil 1 dp equal total dp in coil 1 is 61, total dp in coil number 2, coil number 1 here 35, coil number 2 61. The differential pressure of coil 1 and 2 must be compensated by regulating the corresponding balancing valves ST1 and ST2. That's why we did not substitute ST1 and ST2 when we calculate the dp there. The introduced dp must be equal to the difference between the highest dp calculated circuit 3 and that of the considered branch circuit 1, the dp, and circuit 2, that total dp. So we can obtain static 1 here equal to 83 total minus 35, which we calculated for static 1, and for static 2 we can calculate it. The dp in static 2 will be 83 minus 61, which is 22 kPa. These figures will be calculated for this one and this one after we find the total for each circuit. So ST1 is calculated, but ST3 is considered as from the catalog. So by choosing from the catalog next, when we find this delta P, we can go to the catalog and we can find ST1 is 1.5 with setting 30. ST2 will be 1.5 with setting 70. Okay. Applying now the second calculation system, once the pump is selected, proceed with the differential pressure calculation on the nodes. dpcd, what this meaning? dpcd, which is between this point, dpcd. Okay, this is for this circuit. dpcd equal to C plus coil 3 plus static 3 plus D, which is equal to 52 kPa, and dpab, which is B plus dpcd plus C, which is equal to 86. I'll explain it a little bit. dpcd equal to C plus coil 3 plus static 3 plus D, while dpab is equal to B plus, where is it? B plus dpcd plus C. So already we calculate dpcd. B plus B plus dpcd, which is already calculated, plus E will give you dpab. Compensate or substitute the numbers, you will get 52 kPa in for DPCD and 86 kPa for DPAB. This method is considered to be a static method since we are just consider the less advantaged circuit static balancing valve here and finding out the remaining static balancing valves from the catalogs after we calculate the differential pressure for their circuits for their branches circuits individually. And that's why it is considered a static pre-regulation method. Now, in case we have a variable flow rate circuit with automatic two-way control valves, it is useful to recalculate them with the greater pressure drops, thus containing most of the available overpressure. The remaining part will be eliminated by the balancing valve. It is important, in fact, not to reduce with the series connected balancing valve the entire differential pressure so as not to undo the authority of the two-way control valve. This concept becomes clearer with an example. By calculating a two-way valve with dP 20 kPa, authority is 0.5 and total dP is 40. The control calculation we have an overpressure of 40 kPa at the nodes corresponding to the branch considered. Under such conditions, when compensating for the imbalance with balancing valve by introducing a 40 kPa dP, we could balance the branch, but doing so would greatly penalize the possibility to regulate the valve. In fact, the authority would become beta equal to dP divided to dP total, which is 0.25. If in spite of this we had adopted a control valve having dP 40 kPa and provided the remaining 20 kPa to the balancing valve, we could have obtained such an optimum authority, which is 0.5. If all terminal units of a main column have an excess of differential pressure above a specific value, for example 20 kPa, one can reduce the differential pressure by 20 kPa through the balancing valve installed in the same main column and compensate for the remaining part with the valves installed on the branches and terminal units. To calculate kV, then dPST equal to dPH minus dPr. dPST is the balancing valve pressure drop. dPH is pressure available on the nodes, and dPr circuit pressure drop. Thus, kV equal to 10 multiplied by Q divided square root to dPST. For example, if we have dPH equal to 10 kilopascal, dPr 60 kilopascal, Q equal to 5 square meter, cubic meter per hour, we will have balancing valve dP of 40 kilopascal and kV of 7.9. Now it is only necessary to define the valve setting position, which can be obtained from the technical documentation, which is the catalog. As shown, the setting position, if we go to the catalog, we will find to this kV 7.9, we can obtain 1-inch valve with setting of 100 and with a 1¼ valve with setting of 85, or we can find also another option, 1½ valve with setting of 30. This setting value along with the flow rate value will be indicated on the project after completion of the installation to verify the exact flow rate. The exact calculation of the differential pressure at each terminal unit is certainly complicated, but nevertheless it is absolutely necessary to balance the system. The presetting method or pre-regulation method is a calculation method that corrects any imbalance during design, and of course it is ideal for new systems. However, one must take into account or into consideration that some modifications may be required during installation, even at the last minute, which may vary the contour condition. It is therefore necessary to check all the valves once installed and set, to draw up a detailed report, and if necessary to adjust the setting valve values appropriately. Second method of balancing is the proportional method. This method is recommended in Standard 90.1, ASHRAE Standard 90.1, Energy Standard for Building. This statement there in Section 6.7, Hydronic system balancing shall be proportionally balanced in a manner to first minimize throttling losses. Then the pump impeller shall be trimmed or pump speed shall be adjusted to meet design flow conditions. As already discussed, when multiple terminal units connected to a branch are connected in parallel circuits, any change of the differential pressure value in the nodes may proportionally change the flow rate in all units. So this meaning any differential pressure happened in any node here will affect the flow rate in any terminal or in all terminal also. The balancing procedure in this method required to calculate a rate which is related to the terminal flow, measure the flow, and design flow for this terminal. So simply we will calculate or measure the flow and divide it to the design flow for the same furthest unit. And next step we will install a device, pressure gauge on the static one here to monitor the static. And next step will be we will set the value of differential pressure in the static one to be 95% of RU, which is already calculated for this terminal. So the first step or the first group of steps, let's say, depending on the first terminal, the furthest terminal here, and the static one here. So we will set the differential pressure in the static one into 95% of the calculated U value for the first terminal. Next step, we will do the same in the static 2, but we will consider static 1 value as a reference, and we will do the same in static 2, referring to the static 1. Next step will be static 3, and last step, before the last step, will be static 4, and last step will be static P here. So to best understand this method, let's take an example which will make it very easier to understand the steps of this and how to do this balancing in the proportional method. This is the example for explaining this method. In this example, we have pump specified for 1500 GPM and 70 feet head. These are the design parameters and which we are planning to get in the actual when we are running the system. But when you turn the pump on in the actual operation, if you are not doing balancing, if this system doesn't have any pressure setters or limiters or flow limiters or whatever, doesn't have any balancing devices at all, or doesn't have any limiters for flow limiters, what will happen? If you run the system, you will get actually this system. If you run the pump and all the valves are open, fully open, you will get actually the pump parameters totally different from the design parameters of the pump. You will get 1800 GPM, 64 feet head instead of 1500 GPM and 70 feet head. And you will not get 500 GPM in each terminal or each branch of the circuit. So what to do to solve this issue? And why we are getting actually these numbers? We can see this is the system curve, and this is the pump curve. This is the selected pump curve. Our parameters, design parameters, or our selection or best efficiency point for the pump is here, 1570 feet head. While in the actual, after running the system without any valve, without any flow limiters, we will get this efficiency point, which is not the best efficiency which we are looking for here. So what will happen? The pump will run oversized. The pump will be oversized, and the curve will be the efficiency point will be in this point of the curve, the system curve. So how to solve this issue? We will first of all we will locate the critical circuit here. This is the critical terminal. First, we will start in the critical terminal, the furthest one. We will adjust the flow by using the flow limiters until we get the required flow. Until we get the required flow 500 here, one third of the design flow. And we will next take this reference unit or reference setup here to the next terminal here, and we will adjust it as well to get 500 or one third of the flow. And we will go to the next as well, and we will get here one third of the automatically. Actually, if you do this and this, automatically this one will be one third, but still it is overflow. What will happen next? System is balanced, but the system will be actually here one third overflow will be 587, 587, 587. Still we have overflow on. There is actually different point of design, different I mean it is not in the best efficiency point. At this point actually our system is proportionally balanced, but still have excess flow. The flow total flow is 1760 GPM, while the design flow is 1500. So still we have 260 Uh, okay, now how to drop the value of the flow to the required design flow. We can do that by throttling the valve here. There is valve for the circuit here. We can do this throttling in this valve to get the distributed here to 500, 500, total will be 500 in the valve, 1500 in the valve. So what will happen? Still the pump is running on 1760 while the valve setup is 1500. So what we can do to reach also the pump to 1500, we can trim the pump impeller or add adjust variable speed pump drive the to slow the pump down and remove the extra head in the pump. We have to note that we are now back to 54 feet of head, which is 70 minus 16 equal to 54 feet, which is exactly what we need. And the valve is at our most critical zone is completely open. All zones are proportionately balanced in this circuit, and we actually dropped our brake horsepower to 25 brake horsepower. We dropped it to 25, which is improvement over 36 brake horsepower as a design parameter in the beginning of this circuit. And that's significant when we comes to energy savings, and it's reflective of the kind of energy savings that comes from proportionately balancing the system and making the necessary pump adjustments. The end result is system is vastly more efficient, and you have met an important requirement of ASHRAE 90.1. By this notes, we completed the second commissioning method or balancing method. The proportional method was the second method. Now let's move to the last method, which is the third one, the compensated method. The compensated method can be applied to an existing system and no presetting calculations are required. This method offers two fundamental advantages. First, reduces commissioning and balancing times, as it requires only simple setup for each valve without repetition. Second, reduces pump-related costs, minimizing balancing valve pressure drops. In addition, possible over-commissioning of the pump can be compensated by the main balancing valve. If the imbalance is excessive, it may be appropriate to remove the valve and install a smaller pump or reduce the pump total hydraulic head to achieve maximum energy saving and reduce operating cost. Now there are preliminary actions before we start the procedure of doing this compensated method of balancing. First, we have to identify the main circuit columns, branches, and terminal units on the system project. We have to check the flow rate of each balancing valve. We have to verify that the flow rates of each column are equal to the sum of the ones in their branches. We have to clean the filters and purge the air from the system. We have to open all shut-off and control valves to get the maximum flow rate available. Use if already calculated the presetting values on each balancing valves. If this is not possible, all column balancing valve must be partially separated, excluding only the valve from which you want to start setting the various system unit and areas. You have to make sure that the pump rotates in the correct direction and make sure that we have all the tools required to proceed, which are two differential pressure gauges to instantly read both the differential pressure and the flow rate. And we have also valve setting technical sheet. If the system is very large, at least two people must be able to communicate via mobile phone. There are two main definitions for two types of valves in this method: the reference valve and compensation valve. The reference valve and compensation valve. So, from where this definition came? Normally, in the hydronic balancing, when we change the flow rate through the balancing valve, the pressure drop of that circuit is changed, and consequently, since the hydronic circuits are connected to each other, also those of all branches will be changed. Any disturbance on a branch cause, in fact, a general modification of the flow rate. This behavior of the hydronic circuits makes balancing difficult because after setting a single valve, any change that occurs on the following ones causes variation on the first and in turn in all the others. For this reason, several calibration is required, with a consequent waste of time. Compensated method enables to prevent such a disadvantage, making it possible to perform a one-time setting. So the compensating method is very important. That's why it is saving our time. And to achieve this, it is necessary continuously to monitor the differential pressure of the valve already set up and step by step cancel the changes caused by setting the others by throttling a balancing valve, compensation valve installed upstream of the circuit. So the reference valve is the one which is already we set in the beginning of the commissioning, and the compensating valve or compensation valve is the one which we throttle to compensate the changes in the differential pressure and the flow in the other circuits. So these two definitions are very important to do this type of commissioning. Figure 2.5 shows a branch with multiple terminal units. The furthest unit from production is considered as a reference valve is T1. The flow rate is set to be nominal flow rate for unit 1. This value corresponds to the DPR value that must be continually kept under control. Now switching to the static 2 ST2 setting, returning to the production, we will notice that any change in the unit 2 flow rate will change the DPR. The DPR value therefore needs to return to its original value by acting on the compensation valve. In practice, this means resetting the flow rate of unit 1 to its correct value. The same procedure must be applied to unit 3. The flow rate setting of this branch will also uh, cause a variation in the two previous ones. Okay, the procedure is thus applicable to any number of terminal units served by the same branch. Now, the same branches as well as the columns can be balanced between each other according to the same system. Setting operations must be performed starting from the furthest unit from production reference valve, which moves to the nearest unit. Setting the reference valve. The DP value selected to obtain the correct flow rate in the reference unit should be the lowest possible, while respecting the following limits. Number 1, at least 3 kPa. This minimum value enables to obtain sufficiently accurate readings both with electronic devices and traditional differential pressure gauges. In practice, the reference valve minimum kV must be at least 5.8 times larger than the passing nominal flow rate cubic meter per hour. equal at least valve pressure drop in fully open position. If with nominal flow rate and a fully open valve, the pressure drop is 5 kPa. It is obviously impossible to obtain a 3 kPa setting. The minimum acceptable pressure drop can be calculated with the following equation: dP greater than 10 Q nominal divided to kV maximum square. And last, equal at least to the pressure drop of the most disadvantaged unit when it is clear which it is, and when it is different from the reference one. This situation is typical in line with terminal units featuring very different pressure drops and where the dPr equal to 3 kPa value may not be sufficient to define the differential pressure of the most disadvantaged one. In such a situation, the highest value is required. So we will take the greater value between the disadvantaged one and the reference one. In this method, we have two options of the types of circuit. First, balancing of units with the same dP. All the branches has the same dP. Second option, balancing with units featuring different and unknown dP. They are not the same. This option. So let's go to the first option. First option, the sequence of this example here is developed on a heating system as shown in figure 2.6 here, and what applicable in heating is applicable in other applications, typically in cooling. In this example, we will consider column 6 of secondary circuit static 9 or static 9. So the first step, set the flow rate of the terminal units as shown in the previous paragraph. Second, balance the branches between them. The reference valve In this situation, ST1, which has to be set so as to obtain the nominal pressure drop and hence the nominal flow rate for the branch. We have to fix the balancing valve setting and monitor the dP value dPST1. Then we have to connect a differential pressure gauge to ST1 to monitor the differential pressure in the circuit. We have to make sure that the value read can be constantly verified also by those readings, the ST6 compensation valve. When using an electronic device, a simple extension cable should be sufficient to transfer the reading value, because use of a standard differential pressure gauge will require two people, one here and one here, to monitor the differential pressure in the ST1 and the compensation valve reading. We have to use the ST6 compensation valve knob to maintain the correct DPR value for the ST1 reference valve, the valve heads. If the ST2 and ST3 valves are fully open, they may receive such a high flow that could prevent the desired flow rate to the reference valve DPR. In this situation, ST3 and possibly also ST2 must be divided to obtain this setting. The regulation will be performed in the next step. So next step will be balance the flow rate in the other branches using the second differential pressure gauge, starting from ST2 and proceeding upstream to ST3 etc. At the same time, the dP variation read on ST1 must be corrected through ST6 at each setting variation to ST2 and ST3. Once the last valve is set, so the one closest to the compensation valve, ST3, in this example, all the flow rates will be correspond to the design value. We have to proceed in the same way to set the terminal units of column ST5 by opening it completely and repeat the operations described above, starting from number 2. Once the branches of the various columns are fully balanced, the column must be balanced between them. The procedure is similar to the one used for the branches. The ST4 valve of the last column is considered as reference valve, while ST9 will be the compensation valve. At the end of the procedure, the ST9 pressure drop will represent the excess value of the pump hydraulic head. Should this value be very high, one may replace the pump with a smaller one, or change the hydraulic head value of the circulator. Now here in this circuit, this ST4 is considered to be a reference valve, while ST9 is compensation valve. Second option, balancing with units featuring different and unknown DP circuits radiant systems. The situation when setting the flow rates of branch terminal units, the pressure drops of each unit must be known. This information is generally available in design documentations or in the supplier's technical sheet. This procedure is different from the previous one only for settings of the reference valve. This figure showing a branch with terminal units featuring different unknown pressure drops. The first step, identify the unit with the maximum pressure drop. Number 3 in this example. This is the maximum pressure drop, which is 40 kilopascal. Define the pressure drop of the balancing valve installed on this circuit in fully open position. For example, 5 kilopascal. Calculate the dP at the nodes of the considered unit. For this unit, in this node, number B, or node B is 45 kilopascal. Define the pressure drop for the balancing valve for the first unit, N1, by subtracting the pressure drops of the pipes downstream of unit 1 from the previously calculated dP. In this example, 45 minus 3 minus 20 equal 22 kilopascal. Set valve static 1 to 22 kilopascal and proceed with the other units as described above. For example, static 2, 45 minus 3 minus 10, which equal to 32. And static 4, 45 minus 3 minus 20, which is 22 kilopascal. And last option, balancing with units featuring different and unknown dP. In case of units featuring unknown and different nominal pressure drops, the one creating the highest pressure drop must be identified. This cannot be achieved by simply comparing the actual flow rates of the different units, as some may create short circuit able to absorb most of the flow rate. A limited flow will pass through the furthest units in this situation, and as a consequence, the one with the highest resistance will be absent. Now let's consider once again figure 2.9, assuming the coil pressure drops are unknown. Here, in this example, assuming that the pressure drops here are unknown. So to identify the unit with the highest resistance, we have to follow the next steps. First, we have to open the valve ST5 completely and close all other balancing valves for each terminal unit of the branch, starting from unit 4 and proceeding downstream. So we have to open fully static 5 balancing valve, and we have to open fully, and we start to close for number 1 static 4, which is the closest to ST5. Next ST5 close fully, and we will monitor the differential pressure and reading, and which of them is the highest dP will be dP max. So we have to close the balancing valve and measure the value dP equal dP max. Set the valve so as to obtain the nominal valve flow rate and measure the dP equal to dP minimum. The nominal pressure drop of the unit and its accessories will be approximately dPu equal dP max minus dP minimum. Since the pressure drop are known, it is necessary to proceed as described above. With this slide, we have reached to the end of this presentation. We hope that this presentation was useful to you, and appreciate your time for watching. We have described, just to brief for you this presentation. This presentation was to describe the 3 important methods in balancing of hydronic system, balancing methods of HVAC systems, which are the pre-regulation method, the proportional method, and last the compensation method. Hope this presentation was useful to you, and appreciate your time you spent for watching this presentation, this video. Thank you for watching. Next session will be the components, applications, description, and selection for the valves, and it will be coming to you very soon. Please feedback in the comments. Kindly like, share, and subscribe.